Before we begin 6.2, do you have homework questions? Okay. Well, I wrote myself a couple of notes to remind myself to talk to you about the 4.5 class activities. So the 4.5 class activities were pictures of your platonic solids. So you should have uploaded pictures. There's two sets. So the three platonic solids were the cube, tetrahedron, and octahedron in one set for a class activity, and then the harder two platonic solids go in another class activity. Okay, so that needs to be uploaded by Sunday night. And then on Friday, we're going to need scissors and tape in class and two markers. I'm going to be using red and blue. So for sure you'll need the scissors and tape. You can use a pen if you have to, but the markers will work better. But it's not going to be very fun in class if everybody else is cutting and taping and you're just sitting there bored. Okay, so try and remember, make yourself a note. I always email myself if I have to remember something. Do whatever you need to do to remind yourself, okay? Scissors and tape. Well, in 6.2, we begin by the author's question, can I read into your psyche? So here's what we're going to do. So I'll demonstrate. We're going to take a pencil or a pen and make a squiggly drawing. Don't make it too tiny because you're going to have to read parts of it off. And do it without looking. Don't make it too complicated either because you're going to have to count parts, okay? So see, I'm not looking. I close my eyes and just draw something. And now I'm going to label parts. So you do the same thing. Close your eyes. Don't make it look like mine. So close your eyes. You're not looking at the screen. Just make your own squiggly drawing here. Okay, so paper and pencil out. Making a squiggly drawing. Everybody have theirs made? Okay, now we're going to label parts of it. Okay, so now that you have yours made, put a dot at the beginning and a dot at the end. Okay, whichever you did. Okay, so your squiggly drawing doesn't have to look like mine because we're looking for lots of different examples here, not just mine. Then put a dot. Excuse me. Put a dot wherever the lines are crossing. And then we're going to count the dots. So maybe yours was real simple. Maybe yours was just a line. Then you just have a dot at the beginning and the end of your line. But if you made any loopies crossing, then where they cross, we're going to have a dot. Those are what we call the vertices. So on mine, I have 1, 2, 3, 4, 5, 6. So see how many you have. And then we're going to count the faces or regions. So the outside is one face. Okay, so everybody has one face on the outside, and if you just had a very simple drawing of just a line, that would be all you had. But if your line looped across itself at all, then you've enclosed spaces. So now I have enclosed spaces. I have 2, 3, 4, 5 on mine. So everybody should have the outside one, the big infinite space that you started with, and then any enclosed spaces that you added onto that adds another face or a region. The last thing to count are the edges that join all those dots together. So that's going to be a little more work. For me, it's easier if it's kind of a complicated shape to start where I started and follow through and count that way. So the place between every two vertices is an edge. And I'm not going to count out loud because that's annoying when you're trying to count and I'm counting out loud. So let me just see. So here's where the author starts us off with the question, can I read your psyche? Okay, so here's what I know about all of your drawings. All of your drawings where you have a dot, unless it's the beginning or end dot, you have 4 branches coming out of it. Well, that's kind of lame, isn't it? Because that's how you decide where to put the dot. Okay, so forget that. The other thing that I'll know, it's a little more involved. If you take your vertices minus the edges plus the faces, you will all get 2. Now, if you didn't get 2, then there's something that didn't quite work out. So I'm going to come around and see how you did on counting these. This is something I'd expect you to be able to do on a quiz. So we want to make sure you know how to do this well. It's also your Dropbox activity, so if yours worked out where you got 2, then you can go ahead and work on getting this loaded up to your Dropbox. If it didn't work out, raise your hand, and I'll come around and look, and I'll look at a few anyway to make sure I can hopefully see that you're understanding what's going on. Okay, so you have a squiggly line. Oh, faces. The outside counts as the face. Oh, 1, 2. Don't forget the outside counts as the face. So raise your hand if yours didn't work out. Oh, it's hard to see. Where's your entry? Okay, so you're counting this as like 1. Oh, no. 1, 2, 3. Then there's vertices that go with them. So if you want, you can put a vertice there and there. See when you do that if it works out. 1, 2, 3.
Counted all these wrong, but right.
That comes out to 2.
Edges.
7,
Right.
11, -4.
Cons and smile that. Oh.
Edges.
Oh, okay.
Cheers, back up. You got 2 also? Come out to 2. Come out to 2. Okay, so you know I can't read your mind. So since I can't read your mind, there's a reason for this. This is called Euler's characteristic of connected graphs. So anytime you have a connected graph, which just means you can follow the line all the way around, when you take the vertices minus the edges and add the faces on, you get 2. Here, let me try another one that I'll make up and you see, make sure you know how to do this, okay? So here's one. So you'll be given one on a quiz, so I want you to be able to make sure you know how to do this. So here's that one I'm giving you. Count the vertices, edges, and faces, please. If you don't get 2, then you'll know that you miscounted somehow. So on this particular drawing, there was 4 vertices. Don't forget the dot at the beginning and the end. 2 at 5 edges. So the edges are separated by the dots. And 3 faces. So there's always the outside face. That one people forget to count. So don't forget the outside always counts as a face. It's the infinite region that you're drawing your connected graph on. And any enclosed areas are other faces. Do you have any questions on this? Now, Euler is my favorite mathematician. How many of you have heard of Leonhard Euler? Leonhard Euler lived in the 1700s. He's brilliant mathematicians, on par with any of the brilliant people in other fields you can think of. Michelangelo, Einstein, he's right up there. Euler was so brilliant. Here, let me put this in perspective. I pursued my master's degree so that I could teach math at the university. So I have taken lots of math classes in different areas above the bachelor degree level so that I can teach. If I wanted to go on for my PhD, then I would do research and I would discover something new. So mathematicians have to find some new thing to prove. Like we've been proving in class. So we've done several proofs. Somebody came up with those proofs, and those are the kind of proofs you need to get your PhD. Now, Euler was constantly thinking up new proofs. If I were to get a proof for my PhD, it would take probably 3 to 5 years, and I'd have a paper that was maybe 15 or 20 pages to describe the proof. Well, Euler was so brilliant that he came up with new mathematics on an average of 800 pages per year over a career that spanned 6 decades. So most of us can't even read mathematics that quickly, and here he is coming up with new mathematics at that rate. When they started printing his, at the time of this publication, his printed works weighed 300 pounds, and they weren't done printing out his works yet. And he didn't just focus in one area. Euler was in all sorts of areas. He did acoustics, mechanics, optics, geometry. The reason your math books are written the way they are is because of his notation. He came up with much of the notation we use today. Now he's doing all this while he's going blind. It's supposed to be a painful degenerative eye disease, and at the end of his career he was dictating his work to others to write down. And while this was going on, he was supposed to be a really nice guy. So he's my favorite mathematician, and his work gives us some of the most beautiful mathematics we have. For example, here we have e raised to the I pi plus 1 equals 0. So that's arguably the 5 most beautiful numbers in mathematics, and they're all related to one another, and Euler's the one who discovered how they're related to one another. Well, you might think this just relates to squiggly drawings, which is how we're using it today. But it actually has other ramifications as well. Most of Chapter 6 is outcomes from Euler's characteristics. So there's outcomes in anything that can be drawn representing edges and vertices. So anything that can be drawn there. So here we have graphs. We actually have maps coloring is done using Euler's characteristic of connected graph, because each state can be represented by a vertice, and then you connect them with edges. So anything that can be modeled using edges and graphs can come back to Euler's characteristic of connected graphs. So here in 6.4 we have networking, and we also have finding the best selection of edge choices for the least expensive routes, or the shortest routes, which may coincide. Well, we're going to take a minute to see some questions about what I might ask on a quiz. So I would ask something like this, and I would also ask, if you're given two of those quantities, can you find the third? So on your 3x5 card, you'd want to have the v minus e plus f is 2. So want to use that. And I'll give you some problems where you just have two of these quantities and need to find the third. So let's try a couple of those. So given a connected graph, with 32 faces and 23 vertices, how many edges does it have? Given a connected graph with 32 faces and 23 vertices, how many edges does it have? So you have two of the quantities, and you need to find a third. And I just want to make sure you know the algebra involved in that, since there is no algebra prerequisite for our class. We want to make sure we review that. So you'd start with the v minus e plus f equals 2. And then you'd fill in what you know. So 32 faces, 23 vertices, and we're looking for the e. Okay, so you fill in the two numbers that you do know. Now on the left side of the equation, you'll be able to combine the two numbers. It doesn't matter that the 23 and the 32 aren't next to each other, okay? And the vertices and the faces are both positive. Only the edges are negative. So we add the 23 and the 32 together. So 55. So 55 minus e equals 2. And now you can think about in your head what number you would subtract from 55 to get to, if that's the way you like to do this, or you can actually do the algebra. So if you prefer to do the algebra, whatever you do to one side of the equation, do to the other side. So subtract 55 from both sides of the equation. So we have negative e equals negative 53. And if negative e is negative 53, that means positive e is positive 53. So there's 53 edges. Okay, so you can add up the two numbers on the left. If one of the numbers is the edges, it's going to be subtracted. Let's try another one where one of the numbers is edges. Anybody have any questions on the first one? So given a connected graph, with 40 edges, given a connected graph with 40 edges and 25 faces, how many vertices does it have? So we start with v minus e plus f equals 2. So we'll fill in, we don't know v, so we're going to leave v. We'll fill in the minus 40 for minus e and plus 25. So we're solving for v, And there's two numbers we can combine on the left, so there will always be two numbers on the left you can combine. So in this case, it's a negative 40 and a positive 25, so that comes out to negative 15. So you want the v by itself, and there's a negative 15 next to it. So you add 15 to both sides of the equation. But again, at that point, you could probably do it in your head, right? You can think, what number do I subtract 15 from and get 2? Well, you can do that intuitively like that, or you can just add 15 to both sides of the equation, and that leaves a v on the left and a 17 on the right. Does anybody want to do a third example? Okay, so that's another type of question you can expect on the quiz. But let's take some time to figure out why. The life lesson in this section is one that can be very helpful in a number of areas. The life lesson is to start simple and build up. So we'll go ahead and start simple here. We'll start with the simplest connected graph we can, and we'll add to it, and we'll see if we can understand why, as we made more and more complicated connected graphs, this equation holds true. So there's the simplest connected graph, just a line. So we'll say, we'll count the vertices, edges, and faces there. So the vertices, there's just the 2 points, one on each end of the line, that we add ourselves actually. 2 vertices, one on each end of the line, one edge, and just the one face, because remember the outside counts as a face. The infinite space on the plane that you're putting your connected graph in counts as a face. So 2 minus 1 plus 1, that is in fact 2. So we'll take our first graph now, and we'll make a little more complicated. We'll add another vertex in. Actually, we're adding another edge in. So we'll add a new edge on each step. So the second step has 2 edges. So that means we have 3 vertices now and 2 edges. And we still just have the one infinite exterior face, the plane that we drew our connected graph in. So we're still getting 2. Okay, we're going to add another edge. So the third step, we'll add another edge. So I have 3 edges. But then the question is, do I want the edge to connect to where I started? Or do I want the edge to just kind of be a what we call a pendant edge? It just kind of doesn't form a loop. It just goes off into the face that's already there. So let's look at v minus e plus f on both of these. And we'll keep doing this until we're able to see why the v minus e plus f always equals 2. We'll just add an edge with each step until someone can see why this is happening. So see if you can tell why this is happening. Why is this constantly 2? Here I have 3 vertices, 3 edges, and now I have 2 faces. On the example where my edge was a pendant edge, I have 4 vertices, 3 edges, and I still just have the one face. So at some point, hopefully you can see why is it always 2. We add an edge and we make it more complicated, but we still come out to 2. Anybody seen that yet, why that is? Add another one. Add another one. One more edge. Okay, so we'll add it to the first drawing on the left here. And I'll make it a pendant edge. Or maybe we'll add it to the drawing on the right here. And this time we connect. It looks like it froze, doesn't it? Let's see if I can get that not frozen. So now there are 4 vertices, 4 edges, and this one has 2 faces. Over here there's 4 vertices, 4 edges, and also 2 faces. Anybody see why this is a pattern that's holding consistently? Why we always get 2? Every time they add an edge, the edges go up. Why doesn't the total go up? I'm adding an edge, so the edges go up. Oh wait, it should go down, right? I'm adding an edge, so since I subtract edges, it should go down. It's not going up. It stays 2. Why does it stay 2? Yes?
Does every edge have 2 vertices?
Almost. Yeah, so in this case, you added an edge and you added a vertice. So even though edges went up, vertices went up. This one didn't add another vertice, but this edge added something else. What did this edge add?
Side?
Yeah.
No.
It added a face. Yeah. So every time you add an edge, your edges go up that you're subtracting away, but either your vertices go up or your faces go up. And so that constantly stays 2 then. Well, these were for a single connected graph in a plane. Now we're going to take a look at multiple. I'm going to say multiple distinct connected graphs. Meaning they're separate from each other. So each little graph would be a little connected graph, but we're going to look at 2 at a time, 3 at a time, 4 at a time, and so on until we can see a pattern with that. So if there's 2 of them, suppose we make a real simple one and another one. And now we look at these 2 graphs that are not connected. It probably would be better if I said 2 graphs which were not connected. That'd be a little better language. Let's count the vertices, edges, and faces there. And we're doing it for the combined 2. So the 2 together. So we count the vertices between all of them. Okay, between both of them, I should say. So 5 vertices between them both. And then we count the edges. So 1, 2, 3, 4. And then the faces, there's one region that's outside before we draw our connected graphs. Okay, so there's one region that's outside of both of those. And then there's one loop. So if we look at two graphs together in a plane which are not connected, and we do the vertices minus edges plus faces, we don't get two anymore. So by having these two graphs, we have no longer the Euler's characteristic of connected graphs. So what does that, how does that grow? What happens if you have three? So at your desk, can you draw three? And do what I just did and count the vertices, edges, and faces and see what you get, and then see if the person next to you got the same thing, okay? So remember, these three graphs that you draw are on one face, but other than that, the counting is like what we did before. Don't want you to make them too complicated. You have too much counting to do, so don't make them too complicated. How many did you get? 4? How many did you get? 4? Okay. Anybody else get 4? They should have gotten 4. So the one face, there's one face outside all three, and then I made a loop so I had two faces altogether. If you didn't get 4, that might be where you erred. Okay, go ahead and do 4, and we'll keep doing this until someone can come up with a pattern. Anybody have a number there? 5. Anybody see a pattern?
The combined value always increases by 1.
Mm-hmm. Yeah, it goes up by 1. We add another distinct graph into the plane, and it goes up by 1. Why is that? Shouldn't it go up by 2? I mean, because it was always 2 with the these were always 2 when we just had one connected graph in the plane. It always was 2. Like, shouldn't this with 2 graphs be 4, and then with 3 graphs shouldn't it be 6, and with 4 graphs shouldn't it be 8? Why is it? Yes. Anybody?
One graph equaled 2, and 2 graphs equaled 3. So it's as if every graph. Well, no, that doesn't make sense now. I'd say every graph is like 1, but I don't know.
No, you're right. Every graph is like 1 more, isn't it?
Yeah.
Why is every graph like 1 more instead of just like 2 more? Yeah? No, that's not a hint.
I don't think it's.
Anybody have any ideas? Yes.
I mean, you could have one, like, one of those graphs can't equal one. Could you mathematically have a graph that equals one somehow?
Just by itself, it's going to be vertices minus edges plus faces will be 2. So by itself in a plane, it's always going to be 2. But now when we put several in a plane, well, every time you add one, a distinct connected graph to another distinct connected graph in a plane, it just goes up 1 unit. From 2 it goes to 3 when you have 2, for example. Anybody know why it goes up 1 instead of 2? It's because we're counting everything we counted before, except we only count one exterior region. So before there was one exterior region for one graph, but now there's one exterior region no matter how many we put together in the plane there. So we just go up 1 each time, not 2, because that one plane is the plane that's counting for both of these, or all of these. So this Euler's characteristic of connected graphs actually tells us the answer to how many platonic solids are there. We never did answer that. How many platonic or regular solids are there? So we're going to have to take this two-dimensional work and change it to 3 dimensions. So I'm going to do that by using a balloon. I have a horror of balloons popping. I'm pretty sure my big brother used to chase me around and hit me in the head with a balloon, but I'm just saying that from the results. This whole drawing with a marker on here makes me cringe. Okay. So let's draw a connected graph here. And let's count the vertices, regions, or faces, and edges. Okay, and I'll get a piece of paper to write that on. I guess it'll fit here. Okay, so on a balloon, draw a connected graph, and I still have one outside face, right? I still have one outside face. It's just that that outside face wraps all the way around and makes a sphere, almost a sphere. And then I have 2, 3, 4 faces. On this one I have 1, 2, 3, 4, 5. I had 5 vertices. And 1, 2, 3, 4, 5, 6, 7 edges. Froze again. So the V minus V plus F on the balloon would be 5 minus 7 plus 4. So 2. So that's not really a big surprise. I mean, the only thing that's different there besides drawing on a piece of paper is that your one face curves around. But what helps with the balloon is that we can go ahead and put a platonic solid on the balloon. So let's do the same thing when we put a cube on the balloon. Okay, so I'll put one face on the balloon here. So this isn't square, but pretend it's square. It has some curvature going on. So there's a square, and then I'll put the bottom square here. the bottom face goes here. And then I'll go ahead and connect the corners. I feel like there should be a phobia with balloons. Does anybody else share that? Balloon phobia? Excuse me. No, I don't know. Okay. All right. So now I'm putting the cube on the balloon. And can you see how it's supposed to represent a cube, but it's has one face with the air hole in it. So let's go ahead and write the vertices, edges, and faces of a cube for this connected graph. Okay. So, how many vertices? You remember how many vertices? Can you picture the cube? How many vertices does it have? 8, yeah, vertices. And how many edges? 12. Yep. And faces? 6. Top, bottom, and the 4 sides. So we have 8 minus 12 plus 6 is 2. So we made the cube a little bit rounder, but it's still a cube. And we still have a connected graph, but it's a little bit different in that there's no exterior face, right? Every single face is a face on the cube. So before we had this outside face, but now the face is one of the sides of the platonic solid. So I just did this with a cube because it's easier to draw than any of the others. But you could certainly do this with any of the others. Now, if we flatten this, it turns into a plane. What I mean by that is if we were to take this air hole at the top and stretch it, so we took the air hole that I had at the top and we stretched it, then that side would get all stretched out and be stretched around like this, and be the shape would get drawn out. So this square right here around the air hole would become this square right here, and the bottom square, well, that would be the inside square, and then the 4 sides would be right here. So as long as I put the air hole in the middle of a face, I can stretch out that face and reshape the three-dimensional shape into a flat plane. And then, voila, it's a connected graph. So Euler's characteristic of connected graphs apply to the platonic solids. Euler's characteristics of Euler's characteristic of the connected graphs apply to the platonic solids, because you can draw each platonic solid on something stretchy like a balloon, and then take that air hole and stretch it out so that one face becomes the outside face that we were counting when we counted our graphs. Well, then you take your chart that we did, so let's go ahead and write that chart down. You need it for your quiz anyway, so here you can double check and make sure you have it right. Okay, so you can take your tetrahedron, cube, octahedron, dodecahedron, and icosahedron. you can take those and look at the vertices, edges, and faces and see how the Euler's characteristic of connected graphs applies. So let's just not do the whole thing. Let's do the number of vertices, number of edges, and number of faces. So number of vertices, number of edges, number of faces. And we fill that in on Monday. So the tetrahedron had 4 vertices, 6 edges, 4 faces. So V minus E plus F equals 2. The cube we just looked at, 8 vertices, 12 edges, 6 faces, V minus F. V minus E plus F is 2. Octahedron had 6 vertices, 12 edges, 8 faces. V minus E plus F is 2. The dodecahedron had 20 vertices, 30 edges, 12 faces. V minus E plus F is 2. Icosahedron had 12 vertices, 30 edges, and 20 faces. V minus E plus F is 2. So we had 2 more columns in the original chart, and if you didn't get that on Monday, you'll need to refer to the video for those, for your platonic solids. Well, at any rate, then, because Euler's characteristic of connected solids, Euler's characteristic of connected graphs apply to the platonic solids, that means that we have a way to check, are there any more platonic solids than the 5 that we named? So the last section, the last pages of this section go over figuring out all the different possible ways you can have V minus E plus F equals 2. And it turns out, for the platonic solids, there's only 5 possibilities. So there are only 5 platonic solids. And Euler's characteristic of connected graphs is one way to show that. And you can go through that proof if you'd like to, if that's interesting to you. For today's class activity, though, you'll just need to upload that squiggly drawing that we did at the very first part of the class, right? The one that you drew without looking, okay, and then you started labeling. So just take a picture of that. And then on Friday, please remember scissors and tape, okay? I'll see you on Friday.